Okay, so we're all there, right? This is the one we're working on? Okay, awesome. Okay, so give it a few minutes here so you can get that graphed. Let's see, that'd be about. You guys get something like that? Easy enough to see there? I'm definitely doing a lot of estimating. And thankfully I knew where 3.2 was, but I was kind of estimating the other values. Is that, have you guys confirmed this on your graphic calculator? Does it look about right? I'll connect the dots here. Something like that. Is that working okay for you guys? Yeah? That reminds you, I mean, maybe if you've looked at the calculator, you've seen what this could be. Does this remind you of any kind of a familiar shape? What are you seeing? I feel like Maya really wants to say, but she's having a hard time. Anybody else want to give her a voice? Yeah, it could look like a parabola. I agree. It looks like it just kind of turned around there and maybe is headed back down. Obviously, it's a curvy thing. Conic section for sure. You know, looks maybe like that. Okay. Maybe what we could do. I mean, obviously, you can use the calculator and see this for sure. Maybe we could eliminate the parameter and see what it looks like. That makes sense. Anybody tried that yet? Okay, so when I want to be consistent with you guys, just so it all kind of looks the same. When you tried to eliminate the parameter, did you solve for t in the x equation or t in the y equation?
The x.
X? You guys did that? Okay, so let's do that. So if I solve for t in the x equation, let's see, it'd be x minus 3, t equals x minus, you know what, I'll do it like this. X minus 3 over 2, but it's the inverse cosine of x minus 3 over 2. Okay. Does that make sense? So then we're going to substitute that into the other equation. And the other equation is y equals negative 1 plus 3 sine of the inverse cosine of x minus 3 over 2. This looks pretty crazy, doesn't it? So can anybody tell me, like, categorically, what is the inverse cosine of x minus 3 over 2? Like, what kind of a thing is that? The inverse cosine of x minus 3 over 2. I'm talking specifically about this. Say again? It's an angle. Yeah, specifically that's an angle. And we don't know how many degrees it is, and frankly, we don't really care. We've got the x in there. That's going to throw a serious monkey wrench into the how many degrees or radians is it. The reason why we don't care, though, is because aren't we about to do the sine of whatever that angle is? Does that make sense? So what I'm going to do is build a triangle to help me do this. So I'll just maybe come off to the side here and say the angle that I care about, I'm going to just call it theta, just for lack of a better letter. I'm going to call that theta, and we're going to say that the inverse cosine, or excuse me, the cosine of that angle would be x minus 3 over 2. So that means the adjacent side is x minus 3, and the hypotenuse is 2. And we're supposed to do the sine. And that's going to create a problem with that, right? We're supposed to do the sine of the angle. Sine is going to have us do opposite over hypotenuse. So how do I deal with the issue of having no opposite? I'm insulting you, aren't I? Yes, you're like, do I have to say it? Do I have to? Go ahead and say it. Let's have a conversation. Yes, Pythagorean theorem. You are correct. So let's see here. The Pythagorean theorem, what would it would be? X minus 3 squared. 4, the square root of 4 minus x minus 3 squared? Yeah, okay. So I'll squeeze that in right here. I would suggest we not FOIL that x minus 3 squared. Just leave it as is. Okay. All right, so now we can do opposite over hypotenuse. And so we're going to get y equals -1 plus 3 times this whole mess here. La, la, la. Over 2. All right. Any thoughts on what we could do here? I mean, this is solved for y, and so you could look at this and you could say, well, yeah, this is a function, right? You know, it's like nicely written there, but it's not really recognizable yet. Any ideas on what we could do to get this into a more recognizable form? What's the number one symbol that's bothering you? To get it into the square root, yeah, the square root. So here's what I would do. I would seek to get that square root expression kind of by itself. And so to do that, I would go +1 and divided by 3. That would give me y plus 1 over 3 equals that nice square root expression. And now we are in, I'm going to just swing on down here. We're in a pretty good place to get rid of that square root. If I just square both sides, then I get this. I'm going to come down here and say y plus 1 squared over 9 is equal to 4 minus x minus 3 squared over 4. Okay, is this starting to look a little more familiar, sorta? Okay, there's maybe one last little trick we could do to get this into our more happy form. Anybody see? It's a really simple algebra trick. Doesn't mean it's easy. Don't take me wrong there. It's simple. Maybe it's so simple that it's difficult. Say again?
Can you just divide it through by 4?
Divide the right side?
The rest, like, have 1 minus x minus.
Yeah, like split it up, right?
Yeah.
Yeah, that's it. That's it. So it would be y plus 1 squared over 9 is equal to 1, right? Because 4 over 4 is 1, minus x minus 3 squared over 4. I know I'm right on the edge there. Do you see what it is now? What is it? It's an ellipse. That's right. It's an ellipse. So if I just added the x minus 3 squared over 4, if I just added that over to the left side, it would be a perfect standard form of an ellipse. So I don't know if I got room. I'll just write this on the board here. So if you look at it from that perspective, it would be x minus 3 squared over 4 plus y plus 1 squared over 9 equals 1. It's in that perfect standard form. It is an ellipse. What's the center of the ellipse? 3, -1. Yep. So you look over here at our old graph and you say, all right, if that really is supposed to be an ellipse, does the point 3, -1 really make sense for a center? 1, 2, 3. That makes sense for a center? I'd say so. It looks pretty reasonable, right? And then with this particular ellipse, you look at the 4 and the 9. Based on the 4 and the 9, would this be an ellipse that is more tall and skinny or more short and wide? Tall and skinny, right? Because the bigger number's under the y, smaller numbers under the x. Yeah, so you can see, it's a little harder to see because the x, the half of the x-axis would be 2, and the half of the y-axis would be 3. So it's not like a really huge difference. You know, it's not like you got 4 and 64 where it's going to be like really tall and skinny, but it'll be somewhat, right? It'll just be slightly tall and skinny. So another way of writing an ellipse, right? The other day we looked at, or I think it was Darian, I think we were looking a little bit about how you could write the equation of a circle using parametrics, and this would be a way to write the equation of ellipse even off center. So anyway, that's kind of it as far as graphing these by hand. Yeah, question?
If you had to eliminate the parameter on a test, how far would you want us to take it? Like, would
Right.
you get it to recognize
It's a great
the
question. Yeah, I think it would probably depend on like the objective of what I wanted you to get it to. Like if I wanted you to do this, like if I really wanted you to do this, I would probably phrase the question a little differently. I'd probably say, you know, the parametric equation or parametric equations above constitute an ellipse. Eliminate the parameter and get to standard form to prove that.
Okay.
Right, that kind of thing, if I really wanted to see you doing that. Because otherwise, really, once you got to the y equals with the substitution, you could stop and say, like, that's kind of it, right? The parameter's eliminated and I'm done. So you really wouldn't know where to stop. So if I wanted you to go here, I would kind of force you in there by telling you what it is and then say, all right, now try to get there.
Okay.
Yeah, great question. Yeah, go ahead, McKenna.
So I have a different way of doing it.
Yeah.
And I still get the right answer.
Sure.
I don't really know if it's like right or not.
Let's hear it. Yeah.
Okay, so I like solve for x and y in the original equations.
So they're already solved for x and y,
I mean,
or t.
yeah.
Solve for t, yep.
But I leave the cosine of t and the sine of t the same, so it's like x minus 3 over 2 equals cosine of t.
Okay, so say it again. You said x minus 3 over,
2 equals cosine of t.
okay, yep,
And then we have like y plus 1 over 3
Yep.
equals sine of t.
equals sine of t, yep.
And then I just square each of those and set them equal to 1.
Nice. Now, okay, so if you square each of those, so let's see here. Let me pause this real quick. Let me do this. That's better. Okay, so the length of a curve in parametric form is that right there. Yeah, I'll tell you what. Let me do this really quick. Let me prove this one to you. I'm going to use my tried and true way of doing this. So write this down wherever you want. I'm going to write it right smack in the middle here, but I'll erase it all here in a second. So here would be a way to consider this formula and why it works. So I'm going to draw some random curve here, and it's going to be right there. So if I wanted to find the length of the curve between here and here, what I could do is I could represent this distance right here, this little line segment. I'm going to call that little line segment ds. You guys maybe know that a lot of times S is the letter used to represent distance. For some reason, they've gone with that. I'm going to call that ds, like a little itty-bitty change in distance. And I am going to build a triangle off this. I'm going to call this a little tiny change in x, and this a little tiny change in y. And we are going to consider how we could think about the length of the curve from A to B, from A to B, between those 2 points. So we are going to think about this like a distance formula. So we could say ds squared is equal to dx squared plus dy squared. And then, of course, we'd square root both sides, and we'd get ds is equal to square root of dx squared plus dy squared. And as you guys know, if we want to add up a bunch of these little itty-bitty segments of distance, right, to get the actual length of the curve, that's an integral, right? So I'm going to integrate to get rid of my differential right here. I'm going to integrate both sides. So that's going to give me s equals the integral of square root dx squared plus dy squared. So we're trying to prove that formula up above. So you can see that we're like, I guess I used the letter L up there, and I haven't put my limits in. I guess I'll do that now. I'll put those limits in from A to B, so on and so forth. But I'm missing those DTs, right? DTs are completely gone. So here's how you deal with the DTs. What I'm going to do is multiply both sides by 1, except I'm going to respell 1 in a special way. Does that make sense? Multiply both sides by 1, dt over dt. So the left side, it's going to have absolutely no consequence whatsoever. Like my next step is just going to be s equals. But on the right side, things are going to be a little different. I referred to this earlier, and there was some level of consternation with how this works. What I'm going to do is I'm going to move this dt inside. I'm going to go ahead and multiply it inside my radical. And do you guys remember that if you take something out of a radical, you have to square root it, right? So if you have something that's already outside and you want to put it into the radical, what do you have to do to it? It's going to square it. Yeah, so it's going to basically multiply a dt squared, distribute it into the square root. So I need to actually make this square root a little bit taller. So when I multiply the dt in there, it's going to become dx squared over dt squared, or that. And then the other distributive property would give me dy over dt quantity squared. And then keep in mind, I left this dt out, right? So that dt is still hanging out here, giving us our formula. Does that make sense? So we're adding up a bunch of little tiny ds's, and if we make them tiny enough and add up enough of them, then we'll actually get the length of the curve. Fair enough? Okay, so let me get rid of all that stuff, and we'll use it real quick. It's a very simple equation to use, as you might guess. So if you take a look, it says, set up but do not evaluate an integral expression for the arc length, given by those parametric equations right there. So you've got that formula right in front of you. It does just say set it up, so take a minute, set it up, and we'll check your answer here in a second. This one, it really is kind of a plug and chug setup, right? So we're going to say length of the curve is equal to the integral from, this might seem like a minor detail, but it's pretty important, the integral from 0 to 1. Keep in mind that the thought that we've talked about before, where if we are going to be integrating a definite integral, then the limits of integration have to agree with the independent variables in the integrand, right? So the fact that we have t's for our integrand means that we need to have t's for our limits for this expression to make sense. So give me the integral from 0 to 1, and let's see here, dx dt would be 2t, so 2t quantity squared, plus dy dt would be 12t squared, so 12t squared goes right there, and times dt, and that would be it. This one, I think this one, not going to, we might get ourselves into a little bit of trouble trying, yeah, well, no, actually, no, this would actually be pretty easy to do on paper, but let's just leave it at that, okay? Cool. You guys have any questions about that? Okay, fantastic. Well, let's take a look then at numbers 5 and 6. Graphing these might be helpful. I don't know. We won't do that right away. Let's not do that right away. I don't want you to get too far ahead of us. So let's take a look at number 5, and I want you to think about what the question means. It says, find the leftmost point. So where do you think the leftmost point would happen? Like what else will be going on at the leftmost point? Possibly a vertical tangent line, right? It could be an endpoint, right? Because we do have this domain from -2 to 3. Could be an endpoint, but it very well could be a vertical tangent line. You're not going to, think about it like this, you're not necessarily going to be getting a high point at a vertical tangent line. You might get a high point at a horizontal tangent line, right? So anyways, let's take a look then at number 5. We'll do number 6 kind of with it. I didn't leave myself much room for number 5, but here we go. Find the leftmost point. So if you are looking for a leftmost point, we're going to be considering our candidates. Our candidates are going to include the endpoints, -2 to 3. So we automatically know those are going to be part of our list of candidates. but we got to decide, are there going to be any vertical tangent lines to help us find this leftmost point? So we talked about this earlier. Where are vertical tangent lines going to happen? Yeah, wherever dx dt is 0, but dy dt isn't. Yeah. So let's figure this out. I'm going to figure out dx dt here first. Dx dt is this, 2t plus 2. And I'm going to set that equal to 0. When I do that, I get t is equal to -1. All right, so this is a likely candidate. It is actually in our domain for time, so this could be it. But let's double check and make sure that dy dt doesn't equal 0 there as well. So dy dt is this. And dy dt evaluated at -1, is it 0? It almost is, right? If it was +1, it would be. Yeah, so we can say that this at t equals -1 doesn't equal 0. So that means that t equals -1 is where we have a vertical tangent line, and that's going to be one of our candidates. So then what do I do? Like I've got my two candidates that are endpoints, and then I've got my t equals -1, which is my other candidate. What do I actually do with those candidates to decide which one is going to be where the leftmost point happens? Say it.
Plug them into x and y to get points.
Yeah, plug them into x and y. To be honest with you, I don't even know if we have to plug them into x and y. Looking for a leftmost point. I guess it did say point, so we would want to know both the x and the y coordinate, but the more important one would be x, right? Because we're looking for leftmost. So that's what I'll do. I'll just make a quick table here. My input is t, and my output is x. I've got -2, -1, and 3. So if I plug those into x, what happens? 0. Oops. There we go. What do you think? X coordinates of 0, -1, and 15? Yeah? Okay. So that means my leftmost point is going to be when t equals -1, and so now I want to find the full point, and so I could say the left most point is -1, comma 6? -1, comma 6? Okay. All right, so then, really you think, all right, do I have to justify my answer? Really isn't your work in your table kind of your justification? You're getting all the candidates, you're comparing the candidates with your table, and then picking out the leftmost point. All right. So, could you guys handle number 6, looking for the highest points, giving you that interval from 1.5 to 4.5, and it wants to know the highest point. So this will be our last one for these. So give it a shot. We're getting some stuff about zeros and what's 0 and what's not, and how do we deal with that? Yeah. Okay, fair enough. Okay, so we're looking for the highest point. So the highest point would happen at an endpoint, right? Or where dy dt is 0, and how's that going to work with the dx dt thing? So I'm going to find the dy dt first. So dy dt equals -2 sine of 2t, and we're going to set that equal to 0. So I end up with sine of 2t is equal to 0 when I divide off that -2. So 2t equals the inverse sine of 0, and the inverse sine of 0 would be places like 0, pi, 2 pi, so on and so forth. So I'll list those out. My domain is only positive t, so I'm not worried about any negatives there. I'm going to divide by 2, and I'm going to get t is equal to 0, pi over 2, and pi. And of those, the only two that work would be the pi over 2 and the pi. Does that make sense? Okay, so the 0 is just out of the domain. That's why we would ignore that one. And then I think so if we went 3 pi over 2 would just be slightly high, right? 3 pi over 2 is a little bit bigger than 4.5. So I think we stop at those two, what amount to critical points, or critical times, I guess. So what I'm going to then do is consider dx dt, see what's going on with that. Dx dt is 2 cosine of t. Let's do a quick mental check here and see. Whoops, there we go. Do you guys see that 2 cosine of pi over 2 is 0, isn't it? So that's, potentially kind of a, I don't know, unique situation, right? It could be like a sharp point. They're not always sharp points in those scenarios, but it could be something like that. Later on, we can analyze the graph, but let's go ahead and consider all of these candidates, because you guys realize, of course, that if there is a sharp point, that actually could be the highest point, right? Could be the lowest point, could be the highest point. So it doesn't mean we just give up on that. Just make note of that. Okay, so then I'm going to test these out by taking all my candidates, which are 1.5, pi over 2, pi, and 4.5. And I'm going to be plugging those in for t into the x or the y. What's going to be the more important thing to plug into? And for the y, because I'm looking for the highest point. So I'll put the y right here, and I am looking for the highest point. So I eventually need the x coordinate to go with that. But I'll just leave it at y for now so I can pick out what my answer is going to be. So if you plug in 1.5, you end up with cosine of 3. I know that's almost negative 1-ish. What does that end up being?
Yeah, negative 0.98999.
Okay, something like that. Okay, and then if you plug in the pi over 2, you get cosine of pi, and cosine of pi is negative 1. All right, and then let's see here. We plug in pi, and we get cosine of 2 pi, which is 1. Oops, there we go. And then finally, the 4.5, it's cosine of 9. Again, I don't know what that is.
Negative 0.9.
Oh, you know what? There's symmetry, isn't there? Yeah?
That's
No?
0.911.
911. I tried. Okay. What do you think? So we look at this here and we pick out, and we say, you know what? The highest y value I see is 1, so that's the highest point. So then to find the full point, you would say it's something comma 1. I'd plug a pi in for my x equals 2 sine t. And let's see here, 2 sine of pi is 0. So 0, 1. So did you guys look at a graph of this? What does it look like?
Like a parabola with open downwards.
Okay, okay. Interesting. So pi over, when t equals pi over 2, okay, yeah, interesting. Very interesting. Okay, cool. All right, so as far as that goes, do you guys have any questions?
So why did it not matter when it equaled 0?
So the big caution before was this. Like the way the question was worded, I guess it was yesterday, it said find all horizontal tangent lines of whatever this function is, right? So horizontal tangent lines will only happen when dy dt is 0, but dx dt isn't.
Because it would be undefined.
Because you get some, you're going to get obviously get 0 over 0, which actually is a L'Hopital thing, right? So you might get a sharp point. It just kind of, it's just not going to be a horizontal tangent line because you can't have a vertical tangent line and a horizontal tangent line at the same spot. So you either end up having to do some kind of a L'Hopital rule thing to decide, okay, what is actually going on here? Maybe you have a sharp point. It's just a kind of a wild card, right? You'd have to do some further analysis. In this case, we don't really have to do any further analysis at all because we're really only interested in, as far as high points go, where is dy dt 0 and what are the endpoints? And then you just test those. Those are the only possible high points. So if you test out the where dy dt is 0 and the endpoints, you're collecting all the candidates, even though, to be honest with you, the pi over 2, you can actually see on the graph, the pi over 2 is not even a realistic candidate at all, right? Because you have dy dt equaling 0 there and dx dt equals 0 there. It doesn't look like there's a sharp point on the graph either, right? So this may be one of those L'Hopital rule scenarios where to figure out what it actually is, you'd have to do a limit and evaluate it down like that. Does that make sense? Okay. All right, any other questions? If not, that's it. I'd be happy to hear your questions. So let me get to that.